Hello. In this video, we're going to rush through Riemann sums and discuss the integral, the definite integral, as the area under a curve. So when we started integration, I said the way the textbook goes about it is a little atypical. The vast majority of textbooks would start with this material, and they define the integral this way. I mean, I think pedagogically, it actually makes a lot of sense to do it the way the textbook does it, because, as I say, most textbooks will present this concept as a complicated limit. And then I think a lot of students go through calculus 2, not really understanding conceptually what the integral is. So, introducing it in terms of the net change and only then giving the complicated limit definition probably makes a lot of sense. But here is our situation. We have a function, let's say a strictly positive function, and we want to find the area under the curve. And if you know, taking that literally, the area under the curve is infinite. It just goes all the way down to negative infinity. But what people really mean when they say area under the curve is the area between the function and the x-axis. So think back to derivatives. How did derivatives work? We had something we wanted to know, an instantaneous rate of change. We had something we could easily find, the average rate of change. And we went from what we could easily find to what we actually wanted using a limit. And it's the same concept here. What we want is the area under this curve. We can't find that easily, but something that we can find easily is the area of rectangles. So we'll approximate the thing we want using rectangles, and then a limit. We'll take our approximation and make it exact. And the pictures in the textbook are going to be much nicer than anything I can draw. But here's the idea. We have this region we want. We know how to find the areas of rectangles. That's easy. That's the base times the height. So we take this region we want and we cover it with rectangles. And we can find the areas of all of these rectangles and add them up. And this sum of rectangles is approximately the area under the curve. This sum of rectangles has a name. It's called the Riemann sum. And I am skating through this material. I'm presenting this material, well, it is important, but I'm mainly presenting it to get to something else, something that's more important. So a lot of the technicalities, like the word partition, is not being written down on this page. We can understand this kind of informally. But we've got this sum of rectangles. It's approximating what we want, but it's not giving us exactly what we want. Like the area under the curve includes a little region up here that is not in any of these rectangles. How could we make this approximation better? Well, what if we took this rectangle and we split it into two? You see, we had this big region that wasn't in any of the rectangles. Now part of that region is in this new rectangle. So in general, the more rectangles we have and the narrower they are, the better the approximation is going to be. And if we take the limit of a Riemann sum as the rectangle width goes to 0, as all of the rectangles get thinner and thinner and thinner, this approximation becomes exact. All right. So what does this have to do with integration? Well, it has a lot to do with integration because this area under the curve is also the definite integral from a to b of f of x dx. So geometrically, the definite integral of a positive function is an area. What about functions that are not always positive? What if we have a function that looks like this? So here's f of x. It starts at A, it ends at B. The integral from A to B of f of x dx. Can we interpret this geometrically? Well, if the function is not always positive, then the area turns into the weighted area. You know, we've got this region above the axis, call it A. We've got this region below the axis, call it B. And we've got this region above the axis, call it C. And when I talk about weighted area, what I mean is that we take the areas above the axis and we subtract the areas below the axis. And this, and again, well, as is perfectly appropriate for an applied calculus class, we've skated through a lot of technical details, but the take-home message is, what we stated here, that the area under a curve is a definite integral. So integrals correspond to areas. And that might not seem important, but appearances are deceptive here. A lot of the applications to economics of calculus come in the form precisely of this. There are a lot of economic applications where you care about areas. And we'll see one of those just a little down the line.